right. Good morning again, everybody. Welcome back to the DAC Pavilion. For this morning's Tech Talk, we are happy to have Bob Brennan, Vice President of Customer Solutions Engineering at Intel, and currently a board member for RISC-V International. Bob is going to talk to us today about open architectures to accelerate industry growth. Bob.
Hey, let's see if my mic works. Is it working? Is it working? Yeah, how about that? Cool. Hey. Oh, sorry. I missed you. Sorry. So hello, everybody. I see actually quite a few of my friends in the audience, and I've had somebody who works for me here to applaud at the right points. Hi, Gary. And it's good to see the RISC-V partners in the audience here as well. Today I'm going to talk about the open architectures to accelerate industry growth. We're first going to give you a little bit of a talk about IFS overview, what we do as Intel Foundry Services. We'll talk about the shared industry vision we have working together, the technology that we need, specifically open architecture with RISC-V. We're going to talk about the technology needed, the architecture, the design, the debug and test, and the CAD tools. And lastly, we're going to run through some industry case studies to show you that this is real. So first on our shared vision. Well, I've got to talk to you about IFS since I work in IFS. So in IFS, we offer a broad portfolio of IP to the market. And we offer x86, RISC-V, and ARM cores in our Foundry portfolio. We're ISA agnostic, although we have a special love for x86 in our history there, and an emerging love for RISC-V is established in our booth. We have a customer-centric business model. We customize solutions working closely with our customers, and it's accelerated by the power of Intel at scale. Global manufacturing, global fabs, and worldwide presence. And also Western Foundry, which is very important to some customers. We, as I mentioned earlier, we have this philosophy of any core or accelerator. So in this case, we have x86, AI, or graphics. Any Intel packaging. We've had leadership packaging technology such as EMIB and Foveros on the market since 2017, and we're now offering that out to the world. We have design services where we assist our customers with their designs, SoCs, to run on our Foundry. And we have a broad ecosystem IP offering. We have partners with Synopsys, Cadence, Siemens, you name it. There's a long list of 12,000 IPs in our portfolio, and we're very pleased to work with our partners to offer these IPs to our customers. Gordon Moore, you know, everybody talks about Moore's Law. Everybody talks about the end of Moore's Law. What's interesting to me is that Moore's Law has not ended. In fact, even though Dennard scaling has stopped, Moore's Law hasn't ended. And what's interesting is that Gordon Moore said in 1965, it may prove to be more economical to build large systems out of smaller functions which are separately packaged and interconnected. So Moore actually saw the trailing off of Moore's Law and the point at which we as an industry, we're going to have to segment our designs. Kind of interesting. Dr. Art Degas gave a brilliant talk at ISSCC, I say that correctly. And Art really laid out a beautiful vision for the industry. I can't say it as well as him. But in his talk, Catalyzing the Impossible, he makes the point that for the last 20 to 30 years, we have been working on system-on-chip technology. For the last 20 years that I can remember, we've been trying to integrate more into our silicon. He makes the point that we're moving to an era of SysMore, which is a system of chips. And this is the new breakthrough that we have to all embrace and we have to get behind. So Google published a very interesting blog, I thought. And in this blog, they make the point that computation is moving to domain-specific architecture. Hennessy and Patterson talked about domain-specific architecture, and the Google paper highlights that as well. And by the way, in the back, somebody turn on the timer, please. I have no idea what my time is. So what Google said in this paper is that with the growing demand for AI, the growing demand for video processing, what we need to have is we need to have modularity, optimized silicon and package technology, open standards. We need to have open I/O, open protocols, open security, and open management. And I'd recommend, this talk's going to be available, I'd recommend everybody read that short Google white paper because it really lays out what I think is going on in the hyperscalers in the world. Next, of course, we have the Intel vision. We call this the chiplet revolution. I'm not a marketing guy, but it's nice to be part of a revolution. So in this chiplet revolution, we have interconnect, UCIe. Our intention in developing UCIe was to consolidate the entire industry on one standard. Similar to how we led the disruption with PCIe way back in the 90s, we just want everybody on the same page. And in fact, in UCIe, we invited all of our partners, our competitors, additional foundries, you name it, into our consortium so we can all consolidate on one spec and standard. Compared to PCIe by 16, it's about 20x faster in terms of absolute speed and about 20x more power efficient. Now, this is coupled with what we call our chiplet chassis. And our chiplet chassis could be ARM, RISC-V, or x86. And we see a sea of accelerators customizing Xeon platforms for our customers to optimize their TCO. That's our vision. So interestingly enough, Gordon Moore, Art, Google, Intel. Well, it must be a trend. 4 data points make a trend, right? So why? Why are we all interested in this as a trend? Our motivation is, we have many, but one is the cost of manufacturing optimization. So this graph represents going from a large 300 millimeter squared monolithic die to a 4 chiplet die. Now, there's a lot of assumptions that go into this model. What this graph basically says is if you look on the product cost, which is the y-axis, versus the yield or defect density, is that as your yield improves, as you go towards the right, your defect density gets better and better, it's better to be monolithic. However, until you hit that really, really nice yield spot, in this particular case, there's a 1 sigma variation on this line. The 1 sigma variation of the line shows us that it's better actually in many cases to be in a chiplet. So it depends on what you're looking at. And there's die area, number of chiplets, wafer cost, defect density, a lot of stuff that goes into this. The point is, if you separate your chips, you get better yield on smaller chips. That's the point. Another reason we're going for chiplets as an industry is process technology is becoming highly specialized. So we see this across the world that, for example, I/O technology has thick gate oxide. Analog does not scale with semiconductor process. So what do? Well, we could create a chiplet with I/O technology such that it maintains thick gate oxide and that it doesn't benefit from scaling. So by segmenting that, we specialize the process. Another clear example is RF technology. RF technology is highly specialized. It needs passives and a lot of other stuff. With passive and RF technology, we see that as becoming a separate chiplet. And of course, what Intel loves, the CPUs, the logic memory technology. We want to optimize that on a per process generation. So CPUs want to chase the latest, greatest semiconductor process. They want the performance, they want the power optimization, and so forth. So chiplets let you optimize process technology. Another challenge we see facing us, or we see as an industry facing us, is the AI memory bandwidth gap. What we see happening is, especially in training applications, the need for bandwidth is insatiable. So we developed what's called a roofline model, and we see that in the future we predict these parts are going to want to push and pull 25 terabytes per second. That's a lot of bandwidth. Today, if you look at HBM and HBM3 and HBM scaling, there's only so much bandwidth you can get in and out of your package. Okay, so we're going to need a new chiplet solution to address both the absolute bandwidth requirements and the bandwidth over power requirements. Separately, we see that the memory technology is becoming a thermal hotspot in the system. So as you look at these HBM systems, the memory is consuming a large part of the system power. So what we need to do is figure out how to separate the memory from these chips and turn them into a chiplet architecture that's both thermally efficient and performance efficient. The next motivation is R&D cost and complexity. The number of bugs that we used to get in a microprocessor back when I worked on the 46 was in the order of hundreds. Now it's in the order of tens of thousands. Complexity has gotten out of control. And if you look at the history of engineering all the way back to the 1900s, how do you manage complexity? You modularize and you validate each piece of the system, but you have to architect the overall system so the modular pieces fit together. So R&D, product cost, velocity, and productivity are key motivations. Another motivation is we see people using different types of I/O technology. We see when they want to go inside a motherboard, they have one type of I/O. When they're within a rack, many people use 3-meter cables as an example. And when you're going rack to rack or even in rack, some people really want optical technology. In the case of optical, it's really beneficial, of course, in terms of reach. You can reach further than you could otherwise. And it's also beneficial in terms of latency because you have a better channel model and therefore you have less encoding, therefore your latency is improved. So what we see is the high-speed I/O, the copper, and the optical becoming chipletized in the platform of the future. Okay, technology needed, RISC-V, and we have some RISC-V fans in the audience, and one of them just left, so hey, well, there's 2 of them anyway. Balaji just left. Okay, he's still here, great. So one of the things we see in chiplets is we have to have an open architecture. Everything has to be open. Open RISC-V architecture, open SoC architecture, open manageability, security, you name it. Okay. Currently, there's 2,800 plus RISC-V members, 106 chip vendors, 3 I/O vendors, 18 services. You guys can read. The point is, RISC-V International has become a worldwide phenomenon, and I'm very pleased to be on the board of directors and on the technical steering committee. It's a great bunch of people to work with. As we look at the RISC-V future, and I just met somebody from Semiconductor Research in the hallway, the estimated demand will continue to grow at a rapid pace to more than 60 billion RISC-V CPUs by 2025. And I think Balaji was mentioning today, there's already been 12 billion RISC-V cores shipped worldwide. Now, we see this happening today, for example, in the IoT space. We see a lot of embedded cores. There's one vendor who ships 1 billion cores in IoT space by itself. We see this happening from automotive as automotive transforms to an electrified platform. We see this happening in communication technologies where there's a control plane and a data plane. Control plane is a very attractive place for RISC-V. And we see it also emerging as a possibility in the data centers as the architectures scale up and as the software becomes more mature and attractive to the hyperscalers. So this is what we call the virtuous spiral. And by the way, this slide comes from 1993 in Intel, just so you know. This is the original slide from 1993, and we call this the hardware-software spiral. Okay, so the way it works is probably obvious since everybody knows the x86 story, but the objective here is to standardize the hardware, stabilize the hardware, and that's exactly what we're doing in RISC-V International. We are freezing ISA profiles, and we are working on all the elements of the SoC architecture to make sure that's standardized as well. In addition, we're working with the open software ecosystem, and we're standardizing the stack on the open software ecosystem such that the combination of the open hardware and open software together can create this spiral. And just to accelerate that a little bit, we've created a $1 billion innovation fund where we're seeding companies to accelerate their development and their progress on both RISC-V and RISC-V software. So this is a chipletized system, and there's some elements here that we need to have. We have to have robust end-to-end secure solutions, standardized I protocols, holistic debug solutions, common security architectures, and segment-specific chiplet architectures. So I think data center and edge have a lot of similarities, but they're very different than automotive, ASIL D and B, which is in turn very different than mobile. So I believe we need different chiplet architectures for different segments in the market, and I believe we can standardize base chiplet models for each of these segments in the market. This is a picture of the RISC-V software stack, and this was shown in the board of directors. And I'm pleased to say that the software stack is shaping up very nicely. The different layers of the stack, everything from the tools on the bottom to compilers to virtualization to the application interfaces, is maturing very nicely in the ecosystem. Now we're at a point where hyperscalers can develop their applications on top of this software stack, and we're very pleased to see that progress in the industry. This is our IFS, Intel Foundry Services, RISC-V initiative, and we have Ventana and Esperanto here in the audience. Thank you for being here, guys. I appreciate it. So, don't be offended when I say this. We happen to have Sci-Fi silicon up and running in the lab today, so that came back clean and it's working. So the P550 is working in the lab at about 2 gigahertz plus, I think. Of course, Ventana just presented at the IFS booth with the highest performance single-threaded core. Esperanto also recently presented in the IFS booth, and they have a really cool scale-up AI solution with a unique solution for the memory architecture and managing memory and and so forth. And these gentlemen here can tell you all about it if you'd like to learn more, and biology is here to tell you about Fontana. And our friends in Andes, in Taiwan, have really great embedded solutions. They've been in the embedded business for a long time. So what we've done with our partners, we've joined RISC-V International, we joined DIR-V, which is Digital India RISC-V, and we are participating in standards, and we're partnering with these leaders in the industry through IFS, and our objective is to create an open ecosystem. So for example, the reason we did the Horse Creek Silicon and the board is because we want to have a software development board for the ecosystem worldwide at the end of this year. So I think this is still DAC, which is still Design Automation Conference. Is it still? I don't even remember what it's called. So I think there's some technology needed, and some of you probably in the audience work on EDA technology, I hope, right? So as we go from a system on chip to system of chips, a lot has to change in how we design, architect, and construct these chips. The architecture has to change, the IP and SoC design has to change, the post-silicon and test has to change, and the way we manage system lifecycle has to change as well. So it starts with platform software and hardware co-design, architectural performance modeling, RTL design, all the way down the gamut. Okay, so let's start with optimal silicon partitioning. So this is a tool. There's an open source tool as well. This is just Intel's tool. It's a little dashboard, and you can input your die size, you can input your process technology, and then the tool has all these variables behind the scenes, and then you basically dial in your defect density, and then it tells you what is an optimal chiplet partitioning, in essence, is what it does. So it's a really nice what-if tool. It's not necessarily 4 nines accurate, but architects need to figure out where to partition their designs. So I believe this is something we need as a general tool in the industry. Next, and this is courtesy of Synopsys. Thank you for Synopsys for providing this. There's the concept of shifting left with software and hardware co-design. So the concept of shifting left software is not new. The concept of doing virtual platforms, prototypes, FPGAs, things like this is not a new concept. However, what is new is when we start developing chiplets, we've gone from a monolithic device to a segmented device. So you could argue that what we need to do is just have the software be aware of these different devices, right? You could argue. I would argue that we as the EDA industry and as the hardware industry need to figure out how to make it seamless to the customers. So whether we have this in 1 chip, 2 chips, or 4 chips, the customers just need to look down and see a coherent C that just scales up as you add in chiplets. And that's a big challenge for us. And in order to achieve that, we're going to have to develop new software tools that emulate these distributed systems and show the end customers how to write their firmware and software. So one example of that, and by the way, this is just an Intel example. The EDA industry has many great tools for this. I'm not saying this is the best one. However, it's a nice one in that our Symix virtual platform enables us to create models of our silicon long before it's realized. This enables us to actually connect up to a real-life keyboard, if you'd like to the Symix model. And it enables our firmware, BIOS, and software designers to actually work and run tests and develop their firmware and code on the Symix virtual platform. And that's pretty cool. And like I said, the EDA industry has some other good solutions to this as well. The systems of chips performance modeling is not new concept or technology. System C has been around for, I don't know how long, probably, I've seen people use it for since 2001 was the first model I saw. Probably was developed before that. Anyway, the point is now we are taking a monolithic function where all the buses are running at, say, 1 to 2 gigahertz on die. All buses have very low latency. Now we're distributing that function. So what we have to do is we have to figure out how to do quick segmented performance modeling as we partition the system. For example, if I take X number of units and I break them up into different coherency domains, obviously you're going to pay a penalty in terms of packaging technology, you're going to pay in terms of latency and power and so forth. And the architect has to know that their workload at the end of the day is going to work as intended, right? So the performance modeling tools exist, they just have to be modified to work with chiplets. Next, coupled with that is power and thermal analysis. As I look at systems today, thermal is becoming a huge concern. Rack level density, rack level TCO, rack level throughput is all about thermals, okay? So what we need to do is take this architectural model, which has all the tools for the activity factors of the workload. We need to put that into a thermal simulator, and we need to iterate with the architectural sims, the system power sims, and the thermal optimizations. And we need to run this in a loop until we come out with the optimal solution. So remember, we're optimizing for a multivariable problem. We're optimizing for die size and cost. We're optimizing for package. We're optimizing for thermal and board space, and we're optimizing for performance. So what we need is a tool set that goes between the architecture to system and power thermal optimization that work all together so the architects can play around and get the optimal point for their design. Today this is done, but I can tell you is a very long loop process, right? So today you do your silicon floor planning, you give that over to this group over here, they do these MATLAB simulations, and then eventually they come out with thermal models, right? We need to have a fast iteration, which is different than what we're doing today. Of course, as mentioned in the Google paper, and as I alluded to earlier, we have to have standardized IP, right? So, you know, as Intel, we are leading UCIe in the industry. As I mentioned last summer, we don't have a particular love for UCIe. It's just that we needed to consolidate the industry. The industry was fragmented. There was probably 15 different designs last summer, and we want to bring them together. And currently we started with a physical layer definition and the SIG, which everybody here is welcome to join. And we started with CXL as a protocol. And the reason we started with CXL as a protocol was because it was easiest. It already had security, it already had manageability, it already had all that protocol layer 2 stuff and layer 3 stuff built into it. So that was easiest for us to get to market. However, looking forward, we have to run things like ACE and CHI, coherent protocols, over UCIe. And there's a definition in UCIe that enables us to do this mapping. So this is what we need to do. We need to standardize the HIP and the SIP, and we need to standardize the protocols for how these things work together. Okay. The next thing we need to do is we need to do DTCO and STCO with package design. So this is not an announcement or anything. This is just a showcasing of Foveros Omni technology. Our competition also has some very nice 3D packaging technology. We believe Foveros Omni is a very nice solution for the future. And we're all moving toward direct bonded solutions in the future. As we move to things like Foveros Omni and Foveros direct solutions in the future, we're going to have to evolve the UCIe protocol. So for example, when you're direct bonding your chip to chip, that's a wonderful channel model, but you don't want to burn all the power that you would in terms of a true die-to-die interconnect. So we're going to have a flavor of UCIe that deals with direct connection. So we have to do design technology co-optimization and system technology co-optimization. And we have to do that with our packaging partners, our packaging team at Intel, our IP partners who are developing IP in the ecosystem, and with the people developing the protocols on top of that. All that has to work together and be optimized. Next, and this is a topic that, I don't know, people don't talk about very often, but power delivery is going to be really complicated. So the thing is that if you take a monolithic die and you split it up into 6 pieces, what happens is you get what I call a distributed power delivery droop. So what you'll see is the trace that was nearest to your monolithic die all of a sudden is going a longer distance, and you have droop in the power supply. And this is a bad thing. You do not want droop in your power supply. The good news is that if we optimize chiplets by creating, for example, special I/O die with a thick oxide, that enables us to, in turn, create a special voltage rail for that die, which can accommodate the higher voltage. Correspondingly, as we get to logic die, which are logic die optimized, we can lower the voltage of the input from the power delivery, and we can do more fine-grained power management. So energy burned in a system is under a curve. And with fine-grained power management, you can carefully and precisely manage how much power is needed for a given workload. If you have a tighter voltage tolerance at the edge of your die that's logic only, you can do very nice fine-grained power management. So we have to think about how we do power delivery differently in the future. And also, PMICs have been around for a very long time. We have to optimize PMICs for this solution as well. I don't want to leave out post-silicon platform validation and debug because my validation team would kill me if I didn't mention them. So this is their slide. And what we have today in the monolithic die is we do pretty clever designs. We put in DFT infrastructures, we put in validation infrastructures, we can see everything going on in the chip, and we can actually nudge the clocks and the edges, and we can pretty much adjust any signal you'd like to see on the chip. That's great. Okay, now we have a situation of where we have added complexity to the post-silicon validation suite because previously they could deal with one chip, they could hook it up to the tester, they had a socket, they put it in the socket, they run their test, they run their software, it's all good. Now they have to make sure that that one chip functions accurately and well, and in addition to that, they have to make sure the system on chips works well, okay? Now, this is not unknown science. People have been putting chips together for 30 years. The problem, though, is that we can't afford the time it would take to validate each of the chips independently and then pull them together, right? So we can't do it in a traditional way. So we have to think about a post-silicon DFT infrastructure that spreads across multiple chips and gets them to work together. So validation team, if they're here, don't kill me. I should spend more time on that. Now, I also want to talk a little bit about post-silicon manufacturing and test. You know, the process of wafer sort, die prep, known good die, wafer level and package assembly, test, finish, board develop, you name it. This is a well-trodden path. Okay, well now we're in a situation of, let's say you go from 1 die to 4 die. Now, if you do your traditional flow, you're going to have to get your known good die out, and you have to do that serially. So in theory, if you went from 1 chip to 4 chips to achieve the same thing, you would have 4 times the tester throughput in order to get your chip out the door. So we need to think through how we pull these chips together in test and how we do that such that we don't have to go through this serial loop with chiplets, and that has to change. Now, and this slide is courtesy or source of Synopsys as well, and thank you, Ming, for this slide. So he puts out this very nice framework from implementation, data acquisition, data export, and analytics. So, you know, in terms of test, you have your DFT logic. You've got your scan chain. You have different LFSRs and BIST. You've got your data export. It could be JTAG, USB, PCIe, you name it. And then, of course, you have your analytics on the outside of your port that's pulling all this data together. What's changing right now in the industry that I see, which is very interesting, and I noticed Proteans was over here. I think they have a clever solution, is the people are embedding in-chip monitors into the silicon these days, and they're able to detect real-time PVT droop, as an example. The other thing that we're able to do at scale is the hyperscalers are able to monitor the silicon health in real time, which is kind of cool. And they've applied AI analytics to create predictive failure models of when a piece of silicon may fail. And they've actually been able to predict well when different components might fail and take them out of service before they lose their customers. And what they do is they move the virtual machines off that thing. They have a technician that comes out, pulls out the board, puts in another board, and they're back in business. So I think system lifecycle management and real-time embedded in-chip monitors is a definite trend. And we have to think about how we do this in chiplets. Okay, so now instead of like 1 chip monitor, now you have 4 that have to work in conjunction. Okay, now you have to create standardized data buses and collect all that information, and you have to present that in a way that the AI algorithms can analyze and figure out what's going to happen. So that's a challenge for us moving forward. Okay, so I thought I'd go through some industry case studies here, and I just wanted to mention up front that the Intel examples are real, and the other examples are hypothetical that I've abstracted from talking to probably, I don't know, 100 different customers in the world, and I've tried to abstract the trends of what's going on. So they're not actual designs. So this Lakefield 3D Foveros, this is an example of where you segment the market with chiplets. So this enables us to put different graphics processing in different SKUs of the market. So for example, a Ultra book or a gaming laptop or a desktop all have different graphics needs. And it also enables us to do different memory technologies. Some people may want LPDDR, some people may want DDR, 4, 5, you name it. So there's different memory technologies which we can do with chiplets, right? So for example, in the case of mobile, obviously you want LP5, right? In the case of a desktop, maybe you want D4 or D5, right? So you can segment your market that way. This is Ponte Vecchio, which we've shown this many times before. And it's an example of a super complicated HPC solution. And This is an example of where we did complexity management and process optimization both by segmenting, creating different dies, and packaging them together. So the Ponte Vecchio is a pretty cool piece of computer architecture, I think. Okay, here's another example of I/O optimization. So I spoke earlier about the fact that I/O is going to need to be optimized. So what I think people are going to want is they want to have a UCIe bridge. They want to have a low power SerDes. And that low power SerDes, in some cases, is going to talk to the optical link. And that optical link can run rack to rack. And you can develop your CLOS network, CLOS network, with this optical solution, if you like. Or if you want to run in rack and you want to run copper, and let's say you want to run 224 gig in rack, that's possible as well. So what I see is that people want to just be able to conceptually click in different I/O technologies in their chiplet. Optical is one, high-speed SerDes is another. This is a government case study, and this is a radar beamforming application. This is a real thing that we actually built with the US government. And it's not classified, don't worry, I don't have to take your names. And this is actually with an AIB technology, which is the previous generation chiplet technology. And this is an example, if you look at the block diagram closely, which is probably not possible, but if you squint really hard, what you can see is that the RF and what's going on in this world is they're creating software-defined radios. So the RF is separated, they create software-defined radios. In this case, they've done software-defined radios with FPGAs, and this enables them flexibility in adapting their DSP algorithms as well as different RF front ends. So it's a chiplet example of an FPGA plus an RF front end. This is a case of disaggregated PCIe memory. So this is an example of where you would have, of course, our heroes RISC-V, and of course ARM, our other partners, and you'd have 8 to 64 core CPUs. You would have a NOC, a central NOC, based on ACE or CHI, which is kind of a standardized architecture. You would have common manageability and security. You would have the die-to-die interface on the bottom and top as drawn here. In this particular case, what you could do is you could have a PCIe Gen 4, Gen 5, or Gen 6, depending on your needs, or you could have no I/O depending on your needs. You could also have different DDR technologies. In some cases, you want DDR4 technology because it's more mature technology. The yield is up, therefore the cost may be less. And in some cases, you want DDR5 technologies. It has greater RISC capabilities, as an example. And people want different speeds. So this enables you to, and by the way, DDR4 and 5 are architecturally incompatible. They're very different. So the only real way you can actually do a 2-for-1 design, well, not the only way, but a convenient way to do a 2-for-1 design would be to create a chiplet technology that enables this, okay? So this is a what-if hypothetical. So I mentioned earlier that the bandwidth of HBM is growing. It's exceeding what HBM can actually produce. And I also mentioned earlier that thermals are becoming a big problem. Well, what if you could create a UCIe-based interface that would in turn talk to a logic layer under HBM, and then that would in turn talk to your high-speed memory. And if you think about it, this may look conceptually similar to what Micron did many years ago with their HMC. And if you look at the block diagram, it is somewhat similar conceptually. To that, I'll just say all ideas get built, all good ideas get built eventually. So this is something that could be done in the future with UCIe to help manage the bandwidth and the power density problem that we're seeing in machine learning applications today. This is a case of a multi-core server. We see in the world different types of servers. We see 4-core servers, 16-core servers, 32 cores, 64-core, 128-core, you name it. And the server is a key example of where you want to pick your optimal spot of die size versus power performance. That's a key example. But here you can see that the chassis that I talked about earlier, with a network on chip with ACE and CHI, the manageability and security, the memory architecture, the debug is all the same. So for us, this is what we call the chiplet chassis. The chiplet chassis is standardizing all of these elements together such that people can easily build different type of solutions. This is a case of what Intel calls an IPU. I've been told that I need to call this an IPU. That's the Intel branding. Many in the industry call this a DPU. And the fundamental observation that we have here is that networking and storage are converging. If you think about it, what networking is doing is encapsulating data, okay, and just wrapping a protocol around it. If you think about what NVMe is doing, it's encapsulating data and putting it down to a physical medium. Same with SATA, or same with iSCSI over Ethernet, or same with whatever, right? The point being is that if you make that fundamental realization, and you also realize that CPU cores are very efficient at doing data movement, when you see that together, you say, oh, okay, it makes sense that I'm going to put storage and networking together. So Intel, we have a whole line of IPUs, and I'm seeing this being built across the industry. I'm also seeing RISC-V and ARM cores being used in this application, both as data processing elements. So I see actually very beefy cores being used in this application. I also see them as being used in conjunction with the data movement architecture. So the RISC-V and the ARM cores are the data computation elements, and they're doing a lot of protocol wrapping and unwrapping. And then the DMA elements are well done. Anyway, the point is, some of the elements you see in the system are the same in the other diagram. We have storage acceleration, but we also have ACE and CHI. We have our same NUC. We have our same manageability. And we have the same elements. So we've taken the building blocks of our chiplet chassis and constructed a different application. Now again, the storage acceleration here is unique to this application. The point is modularity and reuse. Last, I'll show you an AI study. I think there's 100 different AI companies running around. It's amazing how many AI companies are in this world. And they all have something unique and different to offer. Of course, Dave's company here is doing the best with Esperanto, right? Of course, yes. Just thought I'd mention because he came to my talk, thank you. But if you look at the fundamental architectures for inference, this is inference, not training, what you'll see is they have a front end, which today is PCI Express. They have a DMA architecture. They have some kind of a scheduler. Then they have a bunch of parallel AI and stream processors. So what I see happening in the world is two things. Number one is, in the case of modular AI or stream processors, a lot of people use RISC-V or ARM cores as a babysitter. And the other thing people are doing is taking RISC-V, and because it's an extensible instruction set, they're either using the vector definition from RISC-V or doing their own to create their own graph or stream processors. And that's one of the things you can do with RISC-V that's very difficult to do with x86 or ARM, because you can't change the ISA, right? So anyway, I see that as a very clever thing that's going on with RISC-V these days. Okay, let's see what else we got. Okay, so wrapping up here. So we are at an inflection point. Whether you believe it's Sys-More era from the Moore era, or you believe it's the Intel chiplet revolution, or you believe it's the Google revolution, doesn't matter. We're at an inflection point. We have challenges here in terms of managing die size, optimizing process, I/O, optimizing R&D and cost. We need open architecture like RISC-V. We need new CAD tools. We need new tools in architecture, design, debug, and test. And the Intel case studies, which are real, and the other case studies, which were abstracted, are real life. Intel examples are real life, and the other examples are where I see the industry is going at this point in time. And so I think this is a big thing that's happening in the industry. So with that, I appreciate your attention, and I'll take some questions. Oh, thank you.
Hey, Bob, I can ask a question.
Oh, you can? Okay.
You were about to escape. You talked about the virtuous spiral and trying to standardize RISC-V, but just now you also talked about the value of customizing the ISA. So how do those two things play together? Is it just within devices that makes sense, or
Sure.
Just get your thoughts?
Yeah, so kindly pointing out the contradiction in my statements about standardizing and freezing ISA versus customizing ISA. So I think the base RISC-V ISA has to be frozen. That's exactly what we're doing in the standards body. And also, because vector processing is becoming very popular, I think we're standardizing that as well. So those two aspects are becoming standardized. And I think in the case, for example, in IoT, they have a lot of vertically integrated solutions that are highly customized. In those cases, they want the standard tools and compilers, but they want to do their vertical application optimization as well, right? So in IoT, that's where they're doing it. And in some cases, like graph processing, the volume of that application is very small, well, relatively small relative to the grand scheme of silicon in the world. In those cases where you have a smaller more niche-y, specialized application, then it's nice to have all the standard tools and add extensions to that. So that's kind of how I see it. So I see kind of as the main things get adopted and grow, that becomes sort of standardized. And then as you have specialized needs, you can extend the ISA. Now it's also possible that they're not contradictory in that as the specialized need grows, then what will happen is that will in turn get to be a candidate to be part of the ISA over time. So hopefully it's not contradictory. So you have a question, sir?
Yes, hi Bob. Chiplet chassis is a pretty interesting concept. So when can we get more information on that? Are you planning to release some reference designs, or are you looking for some industry innovation in that space?
So first of all, we're looking to work with, for example, Google. There was a white paper there on the standards. So we want to standardize UCIe and a bunch of other stuff in RISC-V International and the SoC architecture. And then we're working with selected partners on developing this chiplet chassis. So the elements of the chassis were real, and we have those in Intel Foundry Services, but we also want that the interfaces, for example, debug interface should be standardized in the world. So what we're doing is we're working with partners for their specific application needs, but we're also using our same chiplet chassis. Now we're thinking about doing a reference design, but we'd much rather work with a lead customer and build something real as opposed to, spend a lot of R&D to put a reference design out there. So, but come talk to me, right? So
Yeah,
if you have
sure.
something to build.
One more question.
Sure.
The Intel model that you showed where you can do die disaggregation, does that take into account advanced packaging, yield issues, and things like that?
Yeah, so in that particular model, that was an AMIB case, right? So in that particular model, we have, I don't know which slide it was on, but in that particular model, you have to take into account the cost of the package, right? EMIB is not free, Foveros is not free, right? So you have to take into consideration the package yield, the decreased yield of the package, and so on and so forth. And all of that comes together. But fundamentally, though, if you look at the cost model, yield, die size, and defect density are your primary variables. The packaging becomes a secondary variable in your cost equation in most all cases.